3, 2, 1. All right, let's go. The traditional Tuesday pre-recorded lecture at this point. All right. Okay. So plot for today. So last time we talked about began talking about invertible linear transforms. We remind ourselves that invertibility requires both 1-to-1 and onto. We saw that an invertible matrix gave us an invertible linear transform, and now we are trying to go backwards, essentially. If we have an invertible linear transform, does that mean we have an invertible matrix? And so we're studying invertible linear transforms in general, and we made our first step by proving that a linear mapping is 1-to-1, or injective, precisely when its kernel is trivial. All right, so that was the result we did last time. And today what we're going to do is get necessary and sufficient conditions for the linear mapping to be onto, and that'll lead us to then ask the question of what does a linear mapping do to a basis, and that's where we'll end. And equipped with that, then on Thursday we will finish up the conversation of invertible linear transforms, and that'll be the story. So, alright, that's the plot for today. So, first goal, so last time we proved that the inverse image of a subspace under a linear mapping remains a subspace, and today we're going to push things forward. Recall that if I have a function and a subset of its domain, the image of that under the function is the set of outputs where the inputs are restricted to A. All right, so note the difference. The inverse image, right, is the set of inputs that land in the set. The image is the set of outputs where the inputs are coming from a specific set. All right, cool. All right, so indeed, the image of a subspace is a subspace. So we got two things to prove. First, that T of M is non-empty. All right, well, M is a subspace, so it's non-empty itself, and we know that any linear mapping sends 0 to 0, so 0 lands in T of M, and there you go. All right, next up, I got to prove that T of M is closed under linear combinations. So take two scalars, take two elements. All right, now what does it mean to be in the image? Well, it means you're equal to some outputs for some inputs where the inputs are coming from the set M. All right, so Z is equal to T of X, and W is equal to T of Y. All right, well, then I look at the linear combination of Z and W. Well, Z is equal to T of X, and W is equal to T of Y. And by the linearity, we can suck all of these things inside of T. Now, alpha X plus beta Y lives in M, so that's precisely what it means to be in the image. So this thing lives in the image of M under T, and there you go, two elements that live in the image, and any linear combination form of them remain in the set, so we know we have a subspace. Yay! Alright, so pretty similar setup to what we did last time when we proved that this necessary and sufficient condition for 1-to-1. We proved inverse images of subspaces are subspaces, then we noted that the kernel, the set of inputs that get mapped to 0, is a subspace in its own right. And a similar thing, if you take the set V to be a subspace of itself, which it is, with that lens, the previous lemma reveals that the range is a subspace for any linear mapping. So if you look at the complete set of outputs, that must be a subspace, and note the similarity here to the column space of a matrix. Right, a linear mapping, again, is essentially a generalization of what a matrix does in terms of multiplication. And a cat has shown up, if you can hear him. He's very loud. But yeah, so note the column space similarity here to the range of a linear transformation. Pretty cool. All right, so last time we got a necessary and sufficient condition for 1-to-1 using the kernel, which we noted was similar to the null space. And here we're going to get a necessary and sufficient condition for onto using the range, which is similar to the column space. And of course we know the null space and the column space are fundamental subspaces of our matrix. and play a very important role in a lot of things. And now we'll get our onto conditions. So if I have a vector space and a n-dimensional vector space, so a finite dimensional W, and I have a linear mapping, all right, well, then I'm going to get that T is onto precisely when the dimensions are equal. So the range's dimension is equal to the dimension of W. All right. I want to stress here n-dimensional. So again, when we're dealing with dimensions in this class, we're always sticking to the finite case. It's worth noting that this actually is a situation where it's true for finite, but it's actually not going to be true for infinite, which is an interesting thing. So it's possible to have your ranges dimension line up with the dimension of W, but your mapping fails to be onto. It's kind of an interesting sort of a situation there, right? Is that true? Well, yeah, it's true, yeah. For a second, I was like, wait a minute, what? Yeah, no, it's true. In the infinite dimensional, you can get these things to line up, right? They can have the same in the infinite dimensional case, you can have the same dimension, and you can have a subspace with the same dimension, but they don't equal each other. So, for example, if you're in the polynomials, look at all the polynomials of even degree. That will have the same dimension as all of the polynomials, but they're not equal to each other. So, as we're going to see here, this relies on things being finite rather than the infinite case. So this result does not carry over. So worth keeping that in mind. All right. So again, we're mostly caring about the finite case, but there are these weirdo, like sometimes these things don't carry over to infinite dimensional sorts of things. All right, let's work out the details of this proof. Okay. All right, so if T is onto, then we know that the range is equal to the codomain, so they have the same dimension. They're the same set. Ooh. So the real meat of this proof is backwards. If I know the dimension of the range is the dimension of the codomain, then that they have to be the same set. All right, cool. All right. Now, suppose that we have that the dimension of the range is indeed the dimension of W. All right, well, let's work out the details of why this means T of V and W have to be the same set. All right, well, if the dimension of W is 0, that means that both W and the range are trivial, meaning they are both equal to the trivial subspace, concisely just the additive identity, so they're the same set in that case, and thus they equal out, and there we go. All right. Now, that takes care of that case, so there we get on to, suppose that our dimension is strictly positive, right? It's not 0. All right, well, let's take a basis, y1 to yn, for T of V. Okay, and again, n here is going to be our dimension. All right, now note that since W is also n-dimensional, this has to be a basis for W as well. Right, we pointed that out. If you've got a list of n linearly independent things in an n-dimensional vector space, that must be a basis. If it fails to be a basis, it doesn't span. And if you have a set that doesn't span, you can make you can increase the number of linearly independent things. So here we know we can't do that. All right, so y1 to yn is also a basis for W. So take any element out of y, it's some linear combination of y1 to yn. But what we know about y1 to yn is a basis for the range, so each one of those yks is equal to a t of xk for some x that lives in V. All right, and therefore, now, appealing to the linearity of t, we know y is this linear combination of these y1 to yns, but each one of these is equal to a t x sub k. And then the linearity lets us pull in the linear combo, and there we go. Every element of W is an output for the mapping T, and thus we are onto. All right, beautiful. Cool. All right, so there we go. We did it. Pretty exciting. Yeah. All right, cool. All right, moving right along. So now equipped with this, we've got our mapping, it's linear, and we now have sufficient conditions for both 1-to-1 and onto. So, in order to be invertible, you need to be both. And now we see that 1-to-1 is when the kernel is trivial, and onto happens when the range's dimension is the same as the dimension of the codomain. And again, focusing in on the finite case. Alright, so pretty naturally now we want to go, well, determining onto is precisely asking, well, can we find a basis for the range that has the same number of elements as a basis for W? Right? That would guarantee onto. And so then a natural question is, all right, well, how do I figure out bases for the range? Well, naturally what I would want to do is take a basis for the domain and carry it over. So when can I do that? When can I take a basis for my domain and bring it over to my range? Right. And we will now demonstrate a pair of results that gives us the situation for that, and we'll see now that there's kind of a really deep, intimate connection between 1-to-1 and onto in the finite dimensional vector space case. Now, normally, you can be 1-to-1 and not onto, and likewise, you can be onto and not 1-to-1. But we're going to see something really interesting happens in finite dimensions. It's going to be really neat that there's kind of you're sort of forced to have both of them, and we'll sort of see why that happens. All right. So first off, I want to figure out when can I take a basis in my domain and bring it over to a basis in my range. Okay. So a basis, remember, has two properties. It spans and it's linearly independent. So I want to know, do linear mappings preserve spans? The answer to that is yes. The image of a span is indeed the span of the images. So if I look at the image of a span under my mapping T, I'll just get the span of the outputs. Okay, so spanning sets carry over to spanning sets, no problem. All right, let's prove that. And the proof here is really cool. I love this proof. This proof's got a fun little trick. So let's actually do it. So first of all, let's note that x1 to xn obviously live in the span of the set, and right, they're in there. All right, and here's the trick. This one's so cool. So the outputs live in the image of the span. Okay, now T is linear by hypothesis, and span we know is a subspace. So we know that T, the image of the span under the mapping T, must also be a subspace. But because these things live in there, and we know the span of these is the smallest subspace that contains them, we automatically get this inclusion. We get that the span of these elements is contained in the image of the span. Right, there we go, using that characterization of span as the smallest subspace containing the elements. Pretty cool. I love that. Getting this subset in that direction, it's really cool. Alright, so super slick way of getting that. Now let's go in reverse. I need to prove that any element in this set is an element of this one. Okay. So how is that done? Alright, well, we're just going to pick an element that lives in here. You're equal to T of x for some x that lives in the span of these elements. Okay, well then x is the linear combo of those. And then by the linearity of T, we'll get that y is a linear combo of those things. And there we go, y has to live in the span of those outputs. Alright, so pretty straightforward. Okay, cool. So, right, this inclusion used a pretty slick idea, recalling that spans are subspaces of a certain type. They are the smallest possible subspace. So, pretty cool. Pretty neato. Real neato. And then the reverse inclusion was just sort of a direct argument. Pick an element out of here and just follow your nose. Unravel the definitions. Okay, cool. All right, so we now know that spanning sets will map to spanning sets on their linear mappings, but in order to be a basis, we know that you have to be both spanning and linearly independent. Okay. Now, linear independence, we know, is not necessarily preserved under linear mappings, right? We prove that if I have a basis, you can construct whatever linear mapping you want, and it's very easy to then just destroy the linear independence of the basis you started with. So linear mappings on their own are not going to be preserving linearly independent inputs. However, if you throw in one-to-one, then they are. Now we sort of see why this very surprising connection between one-to-one and onto linear mappings. So now we see that if you've got a one-to-one linear mapping, it's going to send a basis to a basis. So if you also want it to be onto, haha, ooh, interesting. Alright, so pretty cool. Alright, so let's go ahead and do the proof here, and then this is another great example of the kind of proofs that I love, the sort of paradigm of I have all of these hypotheses and they're all getting very sort of explicitly used. So let's work out the details of this proof, and this will be the proof that finishes us off for today. Alright. So suppose you've got a linear mapping and it's one-to-one. I want to show that linearly independent things go to linearly independent things. Okay. All right, well, I want to prove this is linearly independent, so set it up, scale it, add it, set it equal to 0. I want to prove now that my scalars must equal 0. Well, what do I know about my mapping T? I know it's linear. So I can reconstitute the linear combination inside of T. But what do we know about this linear combo? It is equal to 0. And we are linear, we know that we send 0 to 0. So now, since I am one-to-one, and I have these two outputs are equal to each other, I must have that the linear combination of x1 to xn using those scalars is equal to 0, but by hypothesis they're linearly independent. So all of the scalars must equal 0, and there we go, proof is over. All right. So like I said, beautiful proof, right? This is a proof that is exactly like the kinds of proofs that we want to be writing and working with and dealing with, right? I want to show something is true. I set it up, right? It's an implication. I get my linear combo. I set it equal to 0, and then I go, well, what do I know? Well, the pieces involved here come from this linear mapping. And I know linear mappings respect linear combos, and I also know they send 0 to 0. So I now have these two outputs that are equal to each other, and I know I'm dealing with a one-to-one mapping, so I know that my inputs must be equal to each other, and then I get precisely what I need to then invoke this hypothesis. And then that gives me the desired result, that all my scalars are equal to 0. So beautiful, right? We've got vector spaces, so we've got the scaling and the adding of the elements going on. We have a linear mapping, and we are using the properties of linearity. We have one-to-one, which we then use exactly right here. We have assumed the inputs are linearly independent, and that gets used exactly right here. Beautiful. Wonderful proof. Well-oiled machine. All the gears are lining up perfectly. It is... Proofs like these are the best, right? There's no magic, right? There's nothing weird, no goofy inequality showed up, or like, oh, all of a sudden I'm going to do this bizarro algebraic maneuver. Just nice, clean, crisp, follow the definitions, think about what hypotheses we have. It all gets used. It's so good. Love these kinds of proofs, right? Right, it's really been like lately, especially, right? We've got all this machinery we've built up with vector spaces and linear independence and spanning and just all these wonderful stuff, and right, and it's really all coming together and working really well. I love these proofs. These proofs are so cool. All right, and let's cap today off by noting that we equip with the previous propositions. We now know that if I have a one-to-one linear mapping and a basis for V, then my basis, the image of my basis will be a basis for the range, right? We know that a spanning set will carry over accordingly, and now we know under the assumption of one-to-one, linear independence carries over. So if I have a basis in my domain and a one-to-one linear mapping, I will have a basis in my range. And we know the only way you're going to get onto is if the dimension of that lines up with the dimension of W. So in other words, the only possible way we could ever find an invertible linear mapping, the only possible way you can find an invertible linear mapping is, I guess, right, if you have got both one-to-one and onto. Oh boy, isn't that exciting? Well, that idea we should explore a little bit more, and we'll do that next time. So we will cap off the story of invertible linear mappings on Thursday. We're going to bring in a fancy word. We're going to talk about isomorphisms. Ooh. And then we'll finally get around to answering our question from yesterday, which is, all right, well, if I have a invertible linear transformation in Euclidean space, do I have an invertible matrix? The answer is yes, but yeah, we got to finish it off. But we're now in position to do that, and that's what we'll do next time. So I'll see you in person on Thursday.